at least by stating the concept being restream, anyone can access the restream, can watch or share with others. Subsets. Then the closure of at least. Then the closure of at least one set in the sequence. One set in the sequence must have non-empty integer. Non-empty integer must have non-empty interior. Proof. Let AN be sequence of sets. Sequence of sets in the metric space X. Metric space X such that ST means such that capital X equal to union of NAN. Suppose the interior of AN, let interior of AN that equal to null set, means pi is a null set. Then n equal to 1 to here interior A denotes the interior of set A. Interior of set A. Interior of set A. That is AN. That is AN is nowhere dense subset of X. Dense subset of X. Dense subset of X. Since X is open in A1. Since X is open in A1. A suffix 1. Next. So is nowhere dense by the above remark. Is nowhere dense. Nowhere dense by the above remark. By the above remark. We can find an open sphere S1. We can find open sphere S1 of radius less than 1. Of radius less than 1. Which is disjoint from A1. Which is disjoint from A1. Disjoint from A1. Let us consider the concentric closed sphere F1. Let us consider concentric. Concentric means same radius, different, same center, different radius. Concentric circles. Concentric sphere F1 whose radius is half of the radius of F. Whose radius is half of the radius of S1. Now interior of F1. Interior of F1 is open. Is open. And A2 is nowhere dense. And A2 is nowhere dense. Nowhere dense. Nowhere dense. A2 is nowhere dense. A2 is nowhere dense. Hence, interior of F1. Hence, interior of F1 interior of F1 contains an open sphere. Contains an open sphere. Open sphere S2. S2. Whose radius is less than 1/2. Whose radius is less than 1/2. Less than 1/2. And disjoint from A2. And disjoint from A2. Disjoint from A2. Again, consider concentric closed sphere. Again, consider concentric sphere. Again, consider concentric sphere. Again, consider concentric sphere. Concentric closed sphere F2. F2. Whose radius is half of the radius of S2. Whose radius is half of the radius F2. S2, not S2, sorry. S2. Now interior F2 is open. Now interior of F2 is open. Here A3 is nowhere dense. A3 is nowhere dense. Nowhere dense. So above we can find open sphere. Yes. Above we can find open sphere S3. Open sphere S3. Open sphere S3. Whose radius is less than 1/4. Whose radius is less than 1/4. Less than 1/4. And disjoint from A3. And disjoint from A3. Disjoint from A3. Disjoint from A3. Continuing in this way, we get the sequence. continue in this way, we get the sequence. We get the sequence. We get the sequence Fn of closed sets of X. Of closed sets of X such that D of f of n tends to 0. Here, D of f of n denotes the diameter of the f of n. D of n is denoted the diameter of f of n. Diameter of f of n. So X is complete. Since X is complete, by Cantor's intersection theorem, follows that by Cantor's intersection theorem, it follows that Cantor's intersection theorem, it follows that union of intersection of f of n is not equal to null set, means phi. Let X belongs to intersection of f of n, subset are equal to capital X. Subset are equal to capital X. But by the construction of sets, Fn X is not in any of the sets An that equal to 1, 2, etc. Thus we obtain the element. Thus we obtain the element. Thus where small x belongs to capital X, such that X does not belongs to union of An equal to capital X, which is a contradiction, hence the theorem, which is a contradiction. Hence the theorem. Okay. Next, union of bounded theorem. These theorems will discuss open mapping theorem, closed graph theorem will discuss in functional analysis. The uniform bounded theorem 4.6.1. 4.6.1. The uniform bounded theorem. Uniform bounded theorem. Statement. Let B be a Banach space. N is a normal linear space. Is a normal linear space. If Ti is a non-empty, set of bounded linear transformation. Set of BDD means bounded linear transform. LT means linear transformation. Of B into N. Of B into N, having the property having the property that Ti of X is bounded subset of M, is bounded subset of M for each vector X in B, then norm of Ti is bounded set of numbers The Ti is bounded subset of, then Ti is bounded subset of B into B comma N. Proof. Subset of for each positive integer n. Define set f of n follows. Define the set Fn follows. Fn equal to X belongs to capital B such that norm of Ti less than or equal to capital N, small n, for all I. That means norm of Ti minus 1 equal to minus 1 comma n. Then Fn is a closed subset of B for each n. Let Xk be a sequence. Let X of K be a sequence in F of n such that Xk tends to X belongs to capital B. By definition of F of n, we have norm of T of Xk is less than or equal to n for all I. So Ti is continuous. CTS means continuous. Xk such that X, it follows. Xk such that X tends to X. It follows P of I equal to Xk minus T of I X. Therefore, we have norm of T of I X equal to limit X tends to infinity Ti of Xk, that equal to limit K tends to infinity. Here K tends to infinity. Norm of Ti Xk less than or equal to n for all is less than or equal to n for all I. For all I. That means that is is norm of Tix, T of xi less than or equal to n for all I. So hence x belongs to f of n. Thus f of n is closed to n. Oh, we claim that b equal to union of 1 to infinity f of n. Suppose let b is not equal to union of 1 to infinity f n. Then there exists x naught belongs to capital B such that x naught is not equal to fn for all n. This shows that norm of T of x naught is greater than n for all I, all n. Thus, T of x is bounded in B, which is our contradiction. Thus, Ti of x naught is bounded in B, which is contradiction to the hypothesis. Which is contradiction to the hypothesis. Contradiction to the hypothesis that Ti of x is point-wise bounded, each x belongs to capital B. Then B equal to union of 1 to infinity f of n. So hence B is complete. Bayes category by the Bayes category theorem. B is complete. So B equal to union of 1 to infinity f of n by Bayes, just now one proved B-I-R-E-S, Bayes category theorem. So since exists there is n naught such that fn naught is non-empty interior, let us assume that x star is interior point. There exists a closed neighborhood S naught, x star center, and are not greater than 0 such that follows that norm of Ti of x less than or equal to n naught for all x belongs to Sn naught x star and for all I. Then Sn naught x star tends to x star is a closed neighborhood with origin. Is a closed neighborhood with origin. As center. Radius are not. Hence, S equal to Sn naught x star minus x star whole divided by R naught is a closed unit sphere. Is a closed unit sphere. The closed unit. So x belongs to S. This can be written as x equal to x1 minus x star whole divided by R naught, where R naught belongs to S R naught x star. This implies norm of Ti of x that equal to norm of T of x minus x star whole divided by R naught. Now, so that implies that equal to 2n naught by R naught for all I. So here m equal to, let m equal to 2n naught by R naught, 2n naught divided by R naught, then Ti equal to supremum of Ti of x norm x belongs to S, such that x belongs to S is less than or equal to capital M for all I. For all I. Ti is bounded. This completes the proof. This completes the proof. Next chapter. Unit 5. Open operators on Unit 5. Operators on Hilbert spaces. What is Hilbert? A complete inner product space is called Hilbert space. A complete inner product space is called light on. Light on J. Unit 5. Operator on. So self-adjoint operators, normal operators, unitary operators. Adjoint operators. Adjoint operators. Operators on Hilbert spaces. Operators on Hilbert spaces. 5.3. Adjoint operators. Adjoint operators definition. Let T be an open on H. Let T be an open operator. Open operator on H means Hilbert space. You have seen T gives rise to an operator C star. We have seen that T gives rise to an operator. An operator. T star. T star is nothing but conjugate. Conjugate. T star is a conjugate on H star. H star means Hilbert space. Defined by T star F X equal to F of T of X of T of X. X belongs to H, comma, F belongs to H star. H star. T star is also operator here. T star conjugate is also operator. On H star. T double star is the conjugate of T star. T double star is the conjugate of T star. And since H is reflexive, hence H is on H double star. Hence H is reflexive. H is reflexive. H is reflexive. So H double star equal to H. T double star equal to T. Five point 4.3. So 5.4.3, 1.3 around. Yeah, 5.4.3. Statement. The self-adjoint operator. Self-adjoint operator. Before going to this theorem, we'll discuss self-adjoint 5.4. Self-adjoint theorem. Self-adjoint theorem. An operator T on Hilbert space H is said to be self-adjoint T star equal to T. T star equal to T. Similarly, I star equal to I and O star equal to O. Now theorem 5.4.3. Theorem. The self-adjoint operator in DH. The self-adjoint operator in BH. From closed real linear space, closed real linear subspace of BH, and therefore a real Banach space. Therefore, real Banach space which contains the identity transformation, which contains identity transformation. Which contains identity transformation. Proof. Let X be a collection of all self-adjoint operators on Hilbert space. Let capital X be a collection of all self-adjoint operators in Hilbert space H. Hilbert space H. X is a closed linear subspace of BH. Now we prove that X is a closed real linear subspace of real linear subspace of BH. Well, remember, the operator O and I are self-adjoint. The above remark, I and O are also self-adjoint. Self-adjoint. X contains zero operator. Zero is the identity operator. I. X contains zero operator. O and the identity operator I. Identity operator I. X is non-empty. Capital X is non-empty. Let A1 comma A2 belongs to capital X. Then A1 star equal to A1, A2 star equal to A2. For two real numbers alpha and beta, we have alpha A1 plus beta A2 whole star can be written as alpha A1 whole star plus beta A2 whole star. That is nothing but alpha bar means conjugate of A1 star and so plus beta conjugate beta bar A2 star. Here A1, A2 are self-adjoint alpha beta comma reals. Here alpha beta real. A1 comma A2 are self-adjoint. Self-adjoint. Adjoint. Self-adjoints. Self-adjoint. So norm A star equal to A. A1 minus A2 star equal to A1 star minus A2 star. So here, now AN star minus A star, that equal to norm of AN minus A, norm tends to 0 as n tends to infinity. Here to claim A belongs to capital X, we show that A star equal to A. Now A star minus A, that equal to norm of A star minus AN star plus AN star minus AN plus AN minus A is less than or equal to this inequality. You can write A star or minus AN star plus norm AN star minus AN plus norm AN minus A, that equal to norm A minus AN whole star plus norm AN star minus AN, norm AN minus A. That implies this tends to 0 as n tends to this total part, here part, as n tends to infinity. So that is AN star equal to AN, and norm of AN minus A and norm of A minus AN tends to 0 as n tends to infinity. Hence the theorem, hence proved. So next, so linear operators on Banach spaces. 6. Another unit, unit 6. Linear operators on Banach space. Linear operators on Banach space. In this one, operators on equations, adjoint annihilators, Hilbert conjugates. 6.2.1. Definition. Adjoint. 6.2.1 definition. Let capital X and capital Y be normal linear space. A is a bounded linear operator and A is bounded, BDD means bounded linear operator. linear operator from x into y, from x into y, x into y. Let x dash y dash stand for the dual spaces of x and y respectively. Let x dash and y dash stands for the dual spaces of x and y respectively. X and y respectively. So small y dash belongs to capital Y dash, that equal to y dash of ax is a scalar. Define the scalar valued function. Define the scalar valued function. Scalar valued function. F such that x tends to k. K is scalar field. So it is verified that mod of f of y dash of x, that equal to mod of y dash ax less than or equal to norm y dash norm of ax less than or equal to norm of y dash norm x. Norm x. .4. Annihilator definition. What is annihilators? annihilators. 6.4 annihilators. 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 Definition. Let S be a non-empty subset of normal linear space X. Let S be a non-empty subset of normal linear space. NLS means normal linear space X. A functional X dash. A functional X dash belongs to capital X is called an annihilator. An annihilator. Annihilator of S. If X dash X equal to 0 for all X belongs to capital X. Yes. The set of all annihilators. The set of all annihilators. The set of all annihilators. Set of all annihilators. The set of all annihilators of S denoted by S naught. Dually for any non-empty subset. Non-empty subset. Non-empty subset. T of X dash. T of X. We call X belongs to. We call small x belongs to capital X. An annihilator of. Annihilator T if X dash X equal to 0 for all X dash in T. The set of all annihilators. The set of all annihilators of T is denoted by T naught. So short answer question. SAQ. Short answer question. If normal in space I square in the normal linear space I square, find the annihilators of S equal to 1, 0, T equal to annihilators S equal to 0 and T equal to 1, 0 and 2, 3. 2, comma 3. So solution. F belongs to S naught. That implies F is a linear functional. Is a linear functional. Linear functional on I square. So f of 1 comma 0 that equal to 0. That implies f of x1 comma x2 1 comma x2 equal to f of x1 into 1 comma 0 plus x2 into 0 comma 1. That means x2 equal to x2 f of 1 comma 0 that equal to x2 a comma b comma b. Let this is. Conversely, any function f defined I square on I square pi f x1 comma x2 equal to x2 a comma b for constant vector a comma b is a for a constant vector constant vector a comma b is a linear functional on I square. It's a linear functional on I square. So f 1 comma 0 that equal to 0 a comma b that equal to 0. Hence S naught that equal to f I square tends to I such that f of x1 x2 that equal to x2 a comma b for constant vector a comma b. So also f belongs to T naught. That implies f of 1 comma 0 that equal to 0 and f 2 comma 3 equal to 0. That implies f 1 comma 0 and f 0 comma 1 that equal to f of 1 by 3 into 2 comma 3 minus 2 into 1 comma 0 that equal to 1 by 3 f2 comma 3 minus 2 by 3 f1 comma 0 that equal to 0 minus 0 0. That implies f equal to 0. Clearly 0 belongs to T naught. Hence T naught P of 0 equal to 0. So annihilators are. This completes the solution. So now we finished how many? 3 chapters, 2 chapters theorems and the 6th one annihilators, 1 solution. Okay. Next we'll discuss. Next class tomorrow we'll discuss 7th and 8th chapters. Thank you very much.